Hey friends, welcome to the YouTube channel all about electronics. So in the earlier video, we understood that how to perform the binary multiplication. So in this video, let us see how to design this multiplier circuit which can perform this binary multiplication. So here, the multiplication of the two 3 bits number is shown. So here, one number is A2 A1 A0 while the second number is B2 B1 B0. So in the multiplication, we have seen that starting from the LSB, each digit of the multiplier is multiplied with the multiplicand. So here, first B0, which is the LSB of the multiplier, is multiplied with the A0, A1 and the A2. Similarly, this B1 is multiplied with all the bits, and likewise, this B2 is multiplied with all the bits of the multiplier. And during this multiplication, as we move from the B0 to B2, then each partial product is left shifted by a 1 bit position. And once we get all the partial products, then we need to add all these products. So let us design the circuit which can actually perform this multiplication. And here, the circuit which we are going to design is the combinational circuit. So it is often referred as the combinational multiplier or the array multiplier. So here as you can see, this A0 B0, A1 B0, A2 B0 and so on represents the multiplication of the 2 bits. And after the multiplication, the result will be 1 if both bits are 1. But if any one of the bit is 0, then the result after the multiplication will be 0. For example, in this A0 B0, if both bits are 1, then and then only this term will be equal to 1. Otherwise, this term will be equal to 0. So basically, this function can be implemented with the help of the AND gate. That means we can get all these partial products with the help of the AND gate. And once we get all these multiplication terms, then we can add them with the help of the adder circuit. For example, this A0 B1 and A1 B0 can be added with the help of the adder circuit. Similarly, with the help of this adder circuit, we can add this A2 B0, A1 B1 and the A0 B2. That means to design this array multiplier or the combinational multiplier, we need the AND gates as well as the adder circuits. So first, let us start with the 2-bit multiplier and let us see how to design this 2-bit multiplier circuit. So let's say we have a 2-bit numbers, that is A1 A0 and the B1 B0, where this A1 A0 and the B1 B0 represents the individual bit of the two numbers. So this is how we can perform the multiplication of the two numbers. So after the multiplication, the product term will have 4 bits. Because earlier we have seen that when we multiply the two n-bit numbers, then its products can have at the most 2 n bits. Therefore over here, the product will have at the most 4 bits, that is P0, P1, P2 and P3. So this P0, P1, P2 and P3 represents the individual bits of the product term. Now here, we can get each of these partial products with the help of the AND gate. That means here, using the 4 AND gates, we will get this A0 B0, A1 B0, A1 B1 and A0 B1. And as you can see, this P0 is simply equal to A0 dot B0. That means the output of this first AND gate represents the P0. Similarly, this P1 is the summation of this A1 B0 and the A0 B1. So with the help of the 1/2 adder, we can add these two terms. So here, the output of these two AND gates represents the A1 B0 and the A0 B1. So these two outputs are given as an input to the half adder. And the sum output of this half adder will represent this P1 bit. And if any carry is generated during the summation, then it will be propagated to the next stage. So now, this P2 is the summation of the A1 B1 plus the carry which is generated during the earlier summation. So once again, we can add these two terms with the help of the half adder. So as you can see over here, the carry which is generated from the previous stage is given as a one of the input to the half adder. And the second input to the half adder is equal to A1 dot B1. So here, this P2 is the summation of this half adder. And if there is any carry during the summation, then that will act as a P3 bit. So in this way, using the 2 half adders and the 4 AND gates, we can design this 2-bit multiplier. So similarly, let us see the design of the 3-bit multiplier. So as you can see over here, there are total 9 partial products. That is A2B0, A1B0, A0B0 and the so on. So we can generate all these partial products with the help of the AND gate. And as you can see, the final output after the multiplication is of 6 bits, where this P0 represents the LSB while the P5 represents the MSB. So here, this P0 is equal to A0 dot B0. That means the output of this first AND gate represents the P0. Similarly, this P1 is the summation of this A1B0 and the A0B1. So using the two AND gates, we can generate this A1B0 and the A0B1. And using this half adder, these two terms can be added. So the sum output of this half adder will represent the P1. And the carry generated after the addition will be propagated to the next stage. So here, this S represents the sum output of this half adder, while the C represents the carry output. So as you can see over here, the carry output is connected to the next stage. So similarly, this A2B0, A1B1 and the carry generated from the previous stage can be added with the help of the full adder. So as you can see, using the two AND gates, this A2B0 and the A1B1 are generated, and they are given as an input to this full adder. Apart from that, the carry from the previous stage will act as a carry input for this full adder. So here, the sum output of this full adder will be added with the A0B2 with the help of the one more half adder. And the carry generated during the summation will be propagated to the next stage. So here as you can see, the sum output of this half adder will represent the P2 output. And the carry generated during the summation will be forwarded to the next stage. So similarly, in the next stage, using one more half adder, this A2B1 is added with the carry generated from the previous stage. So basically, the carry generated from the A2B0 and the A1B1 will be added with this A2B1. So the sum output of this half adder will be added with the A1B2. So as you can see over here, the sum output of this half adder is given as a one of the input to this full adder, and the second input to this full adder is equal to A1B2. Now here we need a full adder because there is a carry from the previous stage. That means the carry generated from the previous stage will act as a carry input for this full adder. So the sum output of this full adder will act as a P3 bit, while the carry generated during the summation will be given to the next stage. So basically, that will act as a carry in input for the next stage. So in the next stage, using the half adder, this A2B2 is added with the previous two carries. So the one carry which is generated by this half adder is connected as a one of the input to this full adder, while the second carry is connected to the carry in input. And here this A2B2 is the second input for this full adder. So now the sum output of this full adder represents the P4 bit, and the carry generated during the summation will act as a P5 bit. So in this way, we can also design the 3-bit multiplier. So as you can see over here, to design this 3-bit multiplier, we require 9 AND gates, 3 half adders and the 3 full adders. So in general, when we are designing a AND bit multiplier using this method, then we require n square AND gates, n half adders and n times n minus 2 full adders. For example, if we see this 3-bit multiplier, then here n is equal to 3. So here we require 9 AND gates, 3 half adders and 3 full adders. So similarly, if you see the 2-bit multiplier, then for this 2-bit multiplier, n is equal to 2. So in this case, we require 4 AND gates, 2 half adders and 0 full adders. So in this way, using the same method, we can also design large multipliers. So this is the design of the 4-bit multiplier. So this type of combinational multipliers are also known as the array multipliers because it consists of the array of the adders as well as the AND gates. So as you can see over here, for this 4-bit multiplication, we require 16 AND gates, 4 half adders and 8 full adders. Now in place of the half adders, we can also use full adders. But the only thing that we need to do is to set the carry in input of such full adders to 0. So in that case, we will have an array of full adders and the AND gates. Now in this array multiplier, if both numbers are immediately available, then all these partial products, that is A0, B0, A1, B0, etc. will be available after the delay of one AND gate. And once that is available, then all the adders should be able to perform the addition simultaneously. And that is why this type of multipliers are known as the fast multiplier. Because once all the partial products are available after the delay of one AND gate, then all the adders can perform the addition simultaneously. And hence, we can get the product output immediately. But actually if you see, then each adder needs to wait for this carry in input from the previous stage. Because unless the previous stage performs the addition and generates the carry output, the next stage cannot generate the valid sum and the carry output. So although this type of multipliers are fast multipliers, but there will be a carry propagation delay in these multipliers. And because of that, there will be a finite propagation delay, after which we will get this valid product output. So let us do the timing analysis of this 4-bit multiplier and let us find out the delay after which we will get the valid product output. So let's say the TS and the TC are the delay for generating the sum and the carry output of the adder. That means for the each adder, after this TS and the TC delay, the sum and the carry output will get generated. And here, this TA is the delay of the AND gate. So here, after the delay of the TA, the output of the each AND gate will be available. Or in other words, all these partial products like this A0, B0, A0, B1 will be available after the delay of this TA. So here if you see, then this P0 is available after the delay of the TA. Similarly, the output of the each AND gate will be available after the delay of the TA. So here, the sum output of this first half adder or this P1 will be available after the delay of this TA plus TS. Because like I said, after the delay of the TS, each adder will generate the sum output. So here, the output of these two AND gates are available after the delay of the TA. Therefore, this P1 will be available after the delay of this TA plus TS. And similarly, the carry output of this half adder will be available after this TA plus TC delay. But here, because of the space constraint, only TC is shown. Now in the same row, if we come to the second full adder, then it cannot generate the valid sum and the carry output unless the carry in input is available. So in this case, it is available after the delay of the TA plus TC. But like I said earlier, here only TC is shown. That means the carry output of this full adder will be available after the delay of the 2TC. Likewise, the carry output of the next full adder will be available after the 3TC delay. And likewise, the carry output of this half adder will be available after 4TC delay. That means each stage has to wait for the carry from the previous stage. Similarly, in the same row, now let us see when the sum output of the each adder is available. So here, for this full adder, since the carry from the previous stage is available after the delay of the TC, so it can generate its sum output after the delay of the TC plus TS. Likewise, the sum output of this next full adder will be available after the delay of the 2TC plus TS. And likewise, the sum output of this half adder will be available after the delay of the 3TC plus TS. So now, if we come to the next row, then here, this one of the input to this half adder is available after the delay of the TC plus TS. That means it can generate the valid sum output after the additional delay of the TS. Or we can say that its output will be available after the delay of the TC plus 2TS. And of course over here, we need to consider the delay of the AND gate. That means this P2 output will be available after the delay of the TA plus TC plus 2TS. Similarly, it will generate the carry output after the additional delay of the TC. That means it will generate the valid carry output after the delay of the 2TC plus TS. And of course, here the delay of the AND gate is not shown, but actually it will also be there. So now if we come to the next full adder, then its two inputs are available after the delay of the 2TC plus TS. That means it can generate the valid carry output after the additional delay of the TC. Or in other words, it can generate the valid carry output after the delay of the 3TC plus TS. So similarly, the carry output of the next full adder will be available after the delay of the 4TC plus TS. And likewise, the carry output of this last full adder will be available after the delay of the 5TC plus TS. So now in the same row, now the sum output of the each full adder will be available after the additional delay of the TS. So if you see this full adder, then its two inputs are available after the delay of the 2TC plus TS. That means it can generate the valid sum output after the additional delay of the TS. Therefore, its sum output will be available after the delay of the 2TC plus 2TS. So likewise in the same row, for the subsequent full adders, the sum output will be available after the delay of the 3TC plus 2TS and the 4TC plus 2TS. Alright, so now let us come to the last row. So in the last row, for this full adder, this one of the input is available after the delay of the 2TC plus 2TS. But here, the second input is available only after the delay of the TA. So assuming this TA is smaller than this 2TC plus 2TS, it needs to wait for this time. So to be precise, this half adder needs to wait for this TA plus 2TC plus 2TS time. So once that is available, then after the additional delay of the TS, it can generate valid sum output. So here, the sum output P3 will be available after the delay of the TA plus 2TC plus 3TS. And its carry output will be available after the delay of the TA plus 3TC plus 2TS. But here, this TA is not shown because of the space constraint. Similarly, for the next full adder, the two inputs are available after the delay of the 3TC plus 2TS. Therefore, its carry output will be available after the delay of the 4TC plus 2TS. Likewise, for the next full adder, the carry output will be available after the delay of the 5TC plus 2TS. And now, if we see this last full adder, then one of the input is available after the delay of the 5TC plus TS, while the second input is available after the delay of the 5TC plus 2TS. That means this last full adder cannot generate the valid carry output unless the valid carry in input is available. Or in other words, it needs to wait up to this time. So once that is available, then it can generate the valid carry output after the additional delay of the TC. Therefore, it will generate the valid carry output after the delay of the 6TC plus 2TS. And of course, here we also need to include the delay of the AND gate. That means this P7 will be available after the delay of the TA plus 6TC plus 2TS. And similarly, this P4, P5 and the P6 will be generated after the following delays. So as you can see, the maximum delay is required for generating this P6 and the P7 outputs. For example, if we assume that this TA, TC and the TS is equal to 1 unit delay, then this P6 and P7 will be available after the 9 unit delays. So for example, if the 1 unit delay is equal to 2 nanosecond, then this P6 and P7 will be available after the 18 nanosecond. Or in general, we can say that it will be available after the 9 unit delays. So similarly, this is the timing analysis for the 3-bit multiplier. So once again, here if TA, TC and TS is equal to 1 unit delay, then this P4 and P5 will be available after the 6 unit delays. So in general, we can say that for the n-bit multiplier, approximately after the 2n delay, we will get the valid product output of the multiplier. And as the number of bits in the multiplier increases, then this delay will also increase. Apart from that, as the n increases, then the number of required AND gates as well as the adders will also increase. For example, if we take the case of the 32-bit multiplier, then we require 1024 AND gates, 960 full adders and 32 half adders. And instead of the half adders, suppose if we use all the full adders, then we require total 992 adders. So as you can see, as the n increases, then the required number of hardware resources will also increase. And because of that, the power consumption of the circuit will also increase. So although these array multipliers are the fast multipliers, but for the large value of n, they are not preferable. And for that, other types of fast multipliers are used. So in the upcoming videos, we will also see that. Now the array multiplier circuit, which we have discussed over here, can be used to multiply the unsigned numbers. But similarly, in the next video, we will see the multiplier circuit, which can also multiply the signed binary numbers. But I hope in this video, you understood how to design the array multiplier circuit for the binary multiplication. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.